So this is a reminder that we are in Unit 8, which deals with solutions and solubility. The objectives for this video, which is going to be Notes 8.2, are to, number 1, distinguish between a heterogeneous and a homogeneous mixture. We will also be listing the properties for solutions. We're going to not worry too much about this third bullet here, but also be talking about the factors that can affect the rate at which a solid dissolves in a solute, and also explain how freezing point and boiling point are affected for solution. So all 4 of these objectives will be covered in this video. The first thing we're going to talk about has to do with the properties of solutions. As a reminder, a solution is a type of homogeneous mixture. Okay, typically solutions that we talk about are aqueous solutions, meaning they have been dissolved in water, or water is the solvent. So in a solution, the solute particles must have these 3 properties in order to be considered a solution. First of all, the particles have to be very small. Secondly, the particles should be evenly distributed within the solution. And finally, the particles should not be able to be and cannot be separated by filtering. If we think back to previous labs where we filtered our solutions, we were able to use filter paper and drain our solution or drain a substance through that filter paper in order to separate out the solid and the liquid. For a true solution, we are not able to simply filter the substance out. Instead, we would need to possibly heat it or evaporate the liquid off in order to get our solute back. Okay, so we have 2 pictures here. This right here would represent a heterogeneous mixture, a mixture in which we can see all of those individual parts. This beaker right here could be a solution of salt water, which we could represent by this NaClAq, showing that there's some solid salt that has been dissolved in aqueous solution of water. Okay, the particles within this dissolved salt water then are very small. Again, they are evenly distributed, and they will not separate and cannot be separated out by filtering. Okay, in order to help us increase the solubility rates of a substance, so let's say we want to dissolve some sugar in water, we want to dissolve some salt in water, there is ways to increase the rate at which solutes dissolve in solutes. Okay, the first one is to increase the surface area, excuse my spelling mistake here, this should say area, of the solute. Okay, the more surface area there is, the more contact that solvent is going to have with the solute, and thus the faster the solute will dissolve. So if we think about taking a big chunk of salt and throwing it into a thing of water, a beaker of water, it might take a while for that salt to dissolve. If I were to throw that big chunk of salt into that beaker of water and then break it up into smaller pieces, I'm increasing the surface area of that solute, and thus we would expect it to dissolve faster. The second thing we can do is agitate or stir the solution. By stirring the solution, we are increasing, with that movement, the contact between the solvent and the solute surface area. Again, the faster or the longer that solute and solvent are in contact, the faster they will dissolve. And finally, the last thing we can do is we can heat the solvent. Okay, if we gently heat it, we are going to cause those solvent particles to move faster, because we know temperature increases the movement of the particles. The temperature increase then is going to help separate the solute particles from one another more quickly and allow them to come in contact with the solvent particles more readily. So you'll see that with all 3 of these options here, it really has to do with increasing the contact the solvent and the solute have, whether it be increasing the surface area, whether it be agitating or stirring it, or heating the solvent. If we increase the contact that the solvent particles and the solute have with one another, we are going to increase the rate at which those particles dissolve, or increasing those solubility rates. Okay, the next thing we're going to talk about is freezing point depression. Okay, the key point in this, or the key word in this, is depression. And if we think about something being depressed, it's being lowered. So freezing point depression has to do with the idea that the freezing point of a solution is depressed or lower than that of a pure solvent. Okay, so an example here, a pure solvent might be something like H2O. Okay, pure H2O where we just have water molecules present. A solution could be something like we had seen before, NaCl, AQ, where we have water molecules, but we also have a salt in there. And so an aqueous solution of NaCl is classified as a solution. The freezing point of this solution is going to be lower than the freezing point of water alone. So if I were to take a look at my graph down here, I see the freezing point of pure water here at 0 degrees Celsius. Okay, when it talks about molality, that's just a fancy word for concentration of sucrose. This is sugar here. And so you can see as I increase the amount of sugar that I'm adding to my pure water, I will see that the freezing point starts to drop. The reason why is the more solute that I have, the particles are going to interfere with those liquid molecules going into the solid phase. And so it's going to take longer and longer and a lower temperature to get that liquid water into the solid phase. Okay, so the more, there's a direct relationship here between the amount of the solute that you have and the freezing point. So the more solute you have, the greater the effect. And in this word, when we say greater the effect, we mean the lower the freezing point, because those particles are getting in the way of the liquid molecules converting into that solid phase. Okay, the exact opposite of this then to be something known as boiling point elevation. And again, when we think about something being elevated, we want to think about it increasing. Okay, the boiling point of a solution is elevated or higher than that of a pure solvent. So again, a pure solvent might be something like pure H2O. A solution could be NaCl that has been dissolved in water. Okay, once again, the more solute that I have, the higher the effect, or the greater the effect will be, meaning the higher the boiling point. And again, it has to do with the fact that the solute particles are interfering with the liquid molecule's ability to go into the gas phase. So here again, we have the boiling point of pure water at 0. As I increase the amount of sugar that I add to my solution, you will see that the boiling point starts to increase. So by adding sugar or something like salt to a liquid, you are increasing the boiling point of that substance, meaning it's going to boil at a higher temperature. So freezing point depression, boiling point elevation refer to what happens to the freezing point and the boiling point as a pure solvent is turned into a solution, meaning something is dissolved in it.